Good morning. So I'm going to do a quick introduction to the idea of electric fields. Electric fields are associated with the force due to charges, and it's a way of explaining a fundamental problem with any what we call action at a distance forces. In fact, this problem first arose way back in Newton's time when he could not answer to his critics, and he had many critics, that how do planets or the sun communicate to each other that there's this force of gravity? If there's nothing between them and there's no contact, how on earth can one object pull or push on another? So this same problem arises when you talk about forces between charges that are not in contact. How do they communicate? So one solution, so that's the action at a distance it's called. So objects not in contact exert forces. Okay, so what's the problem? How do they communicate? And again, I said that Newton could not give an answer, but he knew his theory of gravity, the GMM over r squared, had something to it because it could predict Kepler's laws of planetary motion beautifully. So the solution is, again, this idea of a field. Objects that have mass, or in this particular tutorial, objects that have charge are in constant contact with an electric field. The key word here is field. It's something that emanates. So what is it? I'm not going to give you super scientific. I like to liken it to an aura, something that surrounds the charge, that radiates out in all directions. It's not material. And what does that aura do? It communicates force, out to infinity, right? There is no end to it. It just grows weaker and weaker with distance. So we've talked a little bit, I think, last year about the idea of aura that might surround people, and you get a sense of somebody just by, seeing them, listening to them, etc. This is another version of it, more literal, though. Okay, so the rest of this is, how do you map a field? How do you show a field surrounding charges? And what are the rules for that? So we want to establish what are the two components of all fields. Well, electric field, again, is trying to communicate force, and a forces, and like all vectors, have two components. That is magnitude. I'm not going to use this pen, it's annoying, and direction. Okay, so I'm going to give you the rules for, more than anything, how you draw the direction of the field, and the magnitude is a little bit more subtle. So we represent fields with field lines. Interesting color scheme here. Okay, so how do we determine a field line surrounding charge or charges? And it's really the same rules for gravitational fields, except it's about mass. So we need a probe. I call it a fly on the wall. A fly on the wall is something that can observe, that can sense without affecting it. Okay? So the standard probe, how do you sense a force due to a charge? Well, you have to have charge. You can't sense force or electrical force unless you have the property of charge. So we need a little probe that has charge, but it's going to be a really tiny charge. So again, the standard is a tiny positive. For whatever reason, physicists chose a positive test charge. And when we start quantifying this, I like to give it a symbol QT. Q for charge, T for test charge. And we're going to see that there's another type of charge called a field charge, which are represented by the source of the fields, let's say in these two cases. Okay, so let me show you how this is done. Don't write anything just yet. I'm going to show you how you can develop a field, and I'm just going to fill it all in. But you got to understand where it comes from. So let's say I have a field charge. I'm going to put a QF right here, and it's positive in this particular case. And we know surrounding it is a field. And if we put a charge in that field, of course, it's going to be attracted or repelled. So if I want to map out that field, I'm going to put my probe, a tiny positive test charge, anywhere in the field and look at where magnitude and direction. So for example, again, don't write anything now. If I put my little positive there, then this positive is going to want to repel it, and since it's close, this is the force vector, it's going to have a big force. If I put the probe right here, a little further away, it's also going to be to the left or excuse me, to the right, just a little less, falling off by this inverse square. If I put the probe there, it's going to be a tiny little vector. But the point is, if I put that positive probe anywhere along this line, the force is always going to be to the right. By using the same reasoning, if I put it right here, then it's going to feel a large force this way, and then if I stay along that line, then it's always going to have a force that way. So rather than draw an infinite number of force arrows, we can kind of combine them and draw field lines. So field lines would emanate to the right if we're to the right of the charge. They would emanate up. They would emanate left. In other words, they would emanate in all directions. So I'm just going to draw 8 directions. And the arrows are indicating not only direction, but the fact that they extend out to infinity. I'm going to stop there. So let's assume these lines go out to infinity. Okay, and there's an infinite number of lines between, etc. So we're going to talk about how you can gauge magnitude in this in a few minutes, but this is the field for any positive field charge. Because we must always probe with a positive test charge, the field lines are always going to be away. They're going to be repelled. So if I have a negative field charge, right, I expect slightly different lines. And again, I take the exact same approach as I did the other one. If I put a positive there, it's going to be pulled in with a fairly large force. If I put it out here, it's going to be a smaller force. Okay, so without going through everything again, it's not hard to figure out that the field lines are for a positive test, or excuse me, for a positive test charge are always going to be inward towards a negative field charge. So these two look very similar except the direction of the field. Okay, so take a look at those. Now, how is a strong field? So in other words, let's say instead of a field charge of positive Q, okay, let's say I had a field line, or a field charge of positive 3Q, 3 times a charge. We would expect, therefore, some 3 times the strength of the field. So how do you show that? Well, the common sense answer that I often hear from students is that they say just make the field lines longer. But that doesn't work because field lines already extend out to infinity. So you obviously can't do that longer. So the alternative to that is simply draw more field lines in relation to some standard. So in this particular case up here, I just happen to draw arbitrarily 8 field lines. So if I were to do it for this one and I wanted to compare it to this one, then I would have to draw 24. And I'm not going to draw 24, but if I want to indicate, so I'm drawing 3 for the up, another 3 for the up and to the left, and so on, and it gets crowded. But that's generally how you indicate a stronger field, is you just draw more lines. And ultimately what you measure about that, I'm really making a mess of this, but you get the idea, is if you look at this, and this is not complete, is that the line density, how close together the lines are, is greater here than it is up here. So how is a strong electric field show field lines? Either more lines, and that's usually if you have something to compare it to, or in general, closely spaced lines, okay? And that's not obvious at all, but it's important. So I'm going to show you a different way you can look at that. I'm going to show you a different color. So let's go back to our negative field charge. Here I just have a field. Where can I see where it's stronger and where it's weaker just in this field without comparing it to something else? Well, I've drawn the 8 field lines and they extend out to infinity, but if I'm here versus here, I expect the one closer to be a stronger field. So how do I actually see that in this map? Well, in a sense, you can look at the spacing between these two versus when I'm out further away, the spacing between these two, you can see that the spacing is much greater. So if the spacing is much greater here, as being consistent with that, it's going to be a weaker field. Okay? So I'm going to do one more, and then I think I'm going to stop because I have another video tutorial that picks up from here. What if you have combinations of charges? Okay? What if I have what is called a dipole? I put a positive here and a negative there. They're in the same vicinity, whereas in the previous page, we will assume that they are completely separate. They're separated by a big enough distance that for all intents and purposes, they're separate fields. Well, we have to draw field lines that shows that these two are attracting, right? A positive field charge and a negative field charge attract each other, so the field line should reflect that, and they should also reflect the direction as well as the strength of the field. So again, don't put anything just yet. What I would do is, let's say I put a positive test charge there. I always probe with a positive test charge. What's going to happen to it? Well, the positive field charge is going to repel it, and the negative field charge is going to attract it. So I've got two force vectors that are going to pull that positive to the right. And in fact, anywhere along this line, right, it's the positive test charge is always going to feel a force to the right. So that gives me a clue as to what my first field line is. That's the simplest one to understand. Is going to be a field line that directly connects the positive to the negative. And you can see that now that kind of shows attraction. Now, if I move off this axis, it gets a little more subtle. So again, let me try to develop it before you draw anything. Let's say I put a positive right here. Okay, it's going to feel a pretty strong repulsion that way due to the positive, and it's going to feel a weaker attraction to the negative. So the field line is going to be the vector sum of these two, which will be something like this. And then if I move the positive test charge, let's say in the middle, again, this is getting kind of busy, so let me erase some of this. And I'm just going to put the field line I just drew like this. If I put my positive, let's say right here, then the positive here, again, is going to repel. The negative is going to attract with the same force because it's equidistance between the two. So the net result is going to be a vector like this. And if I move the positive a little closer to I'm going to get a vector that's like this. Okay, so if you're confused, I apologize. I can understand why. But if I do that for all the positions along that, I'm going to get a field line that looks like this. Okay, it's going to curve around. And if I go below, I get some bisymmetry. I'm going to get something like that. And if I go a little further away, I'm going to get a field line that loops there, but notice there's a big spacing between here and here, indicate that it's weaker here and here than it is between here and here. And then again, by symmetry. And notice my field lines always go away from the positive and towards the negative because we're always probing with a positive. Now, what about the rest of the space? Well, if I start here, the positive test charge is going to be attracted in. It's going to be repelled by this, but much weaker than attraction here. So there's going to be a field line coming in. And then if I go here, it's going to be going out. And then I might have something like this, something like this. And these don't have to come back. These will go out to infinity. And then I'd have something similar there. So that's what the field line looks like around a dipole. Okay, so we see attraction. And if we look off to the left here, it looks very similar to what we saw for a naked positive test charge, and the same thing with this one. Okay, so I will stop here. There will be another tutorial that picks up on this. It's fairly abstract, but it's not too hard to understand.